In this lab, the wind tunnel is used to examine the flow around the cylinder body. The once uniform flow is obstructed as it passes the cylinder, causing vortices and pressure deviations around the cylinder. At significant Reynolds numbers, the drag caused by a cylinder inflow is primarily caused by pressure deviations, as flow separates from the surface of the object. This can also be called pressure drag. From this figure, one can deduce that the coefficient of drag should generally go down with increasing Reynolds number, although this does not mean that drag force will go down with an increase of Reynolds number. The objective of the experiment is to see how Reynolds number and surface roughness influences the flow around the cylinder, the CP and the CD. By adding turbulence to the flow with a trip strip, it is hoped that the drag will be decreased. This concept is widely tested and is known to work. It has been applied to golf balls like the divots on this picture and to the automotive industry as seen in this picture. We used a few different pieces of equipment for this experiment, the wind tunnel being our main one. It was used to create the test environment. This diagram shows the relative position of the cylinder within the test section. The modified cylinder is about 11.7 centimeters in diameter and has 24 static pressure ports equally distributed around the circumference of the cylinder, so basically a port every 15 degrees. This was used with the scanning valve to collect pressure data. For the trip strip, we used 1 to 2 millimeters in diameter plastic wire, which spanned the area at which the pressure ports were located on the cylinder. This diagram shows our cylinder setup. To visualize the flow, we used the fog machine provided and the laser sheet. All testing was done in the Cal Poly low-speed wind tunnel between the hours of 6 and 9 p.m. on March 1st, 2017. The temperatures ranged between 17 and 14 degrees Celsius, which was a gradient caused by the rapid cooling after sundown. This can be noted for errors, but the actual tests were done in rapid succession of each other, therefore the temperature change was neglected. Before we collected any data, we set LabVIEW to receive 100 data points from each pressure port. The data was collected with a period of 200 and an average per frame setting of 10 and 20. Next, the ambient conditions were recorded for the wind-off data. After going through the safety checklist required before running the tunnel, the RPM was set to 300 and the tunnel was switched on. After a 20-second settling time, 3 different data sets were taken for repeatability purposes. The RPM was then increased to 600, where we also collected 3 data sets after a settling period. Each data set we had consists of 24 static pressure readings equally distributed around the cylinder, with the first being the stagnation pressure.
Looking at the wake, we can see the von Karman vortex-anti-vortex pairs that form the vortex street. Running the tunnel at 100 RPMs, we recorded the flow and slowed down the video in order to count the oscillation frequency of the flow. We counted 44 up-down oscillations in 8 seconds. This gives us a frequency of about 5.5 hertz. We then multiplied this frequency by the diameter of the cylinder and divided by the velocity. This gives us a Struhal number of 0.609. We hope to see the boundary layer separating and observe the backflow that causes small vortices. It was hard to visualize the boundary layer because it was difficult to align the smoke at the inlet with the leading edge of the cylinder. For most of our tests, the smoke was seen moving around the cylinder, but not touching it. The smoke follows streak lines. As the smoke enters the test section, the flow is steady, so the smoke also accurately follows the stream and path lines. When the flow reaches and interacts with the cylinder, the velocity vector field that describes the motion of the fluid changes over time. The flow is now unsteady, but the boundary layer tends to stay laminar and moves about the surface. The flow then separates, leaving a chaotic turbulent wake behind it. There are 2 stagnation points, one at the very front of the cylinder and one at the trailing edge. Faulty ports may have caused false data, which actually happened on our first day of testing. The data collected on that day showed obvious signs of errors, and a second day of testing was required to get reliable data. Another possible source of error may have been that the wire was not in contact with the cylinder. Air may have been flowing in between the wire and the cylinder, and this is what we are attributing to the low pressure readings directly after that bottom wire. We also could not get reliable data from low RPMs. Another source of error could be due to the fact that the flow was already transitional or turbulent by the time it reached the cylinder.
In our analysis, we used the following equations: coefficient of drag, coefficient of pressure, Reynolds number, and force of drag.
This plot clearly shows there is less drag force in the cylinder with a trip strip for all RPMs tested. It is also worth noting that test 1 and test 2 yielded very consistent results. The coefficient of drag is dependent on the Reynolds number of the flow, which is why the values are not the same for each RPM tested. Although the important thing to take away from this plot is that the coefficient of drag is much lower for the cylinder with the trip strip. This illustration shows that without a trip strip, the flow separates early, creating a larger area of low pressure behind the cylinder, which is why the drag force is higher. Comparing the previous image with this one, it is clear that the turbulent flow regime separates later and results in a smaller area of low pressure than the smooth cylinder. In conclusion, this experiment tested the theory that the coefficient of drag should decrease as Reynolds number increases. The experiment also analyzed the effect of surface roughness on the coefficient of pressure and drag. The results of this lab show that the coefficient of drag decreases with an increase in Reynolds number. It was also proven that the coefficient of drag decreases with the addition of a trip strip. Low Reynolds number cannot be observed in the wind tunnel because the fan causes too much disturbance and it would require a denser fluid. The addition of a trip wire did affect the pressure drag on the cylinder, both at 300 and 600 RPM. We saw a decrease in drag for the tripped cylinder. Although a change in coefficient of drag was seen with a decrease in Reynolds number, the difference was not significant enough to produce a trend.